So in this presentation, I will be discussing the design of packed columns for separations, especially focusing on absorbance. So far, in this course, we've assumed that whenever we have multi-stage separations, we're using some sort of a tray. And so we have an integer number of trays where each one allows liquid to flow over it and vapor to come up through holes in the trays in a controlled way so that you get good vapor-liquid contact. And this is a common separation method for distillation. But there's a better way to do this for some applications, and that's a packed column. In a packed column, what this illustration shows is what you would have for a scrubber, where you've got contaminated gas coming in at the bottom, and there's some space there and some additional hardware to allow there to be just room for flow to happen. And then you go into this section of the column where there is packing. And in this packing, you have some screens to hold it in place. But basically, it's a random packing of these little objects of a certain shape, and they're usually inert materials such as ceramics, plastics, or maybe metals like stainless steel. And then once you go through that packing, this is where the vapor-liquid contact is supposed to happen. And then above that, you get rid of any entrained liquid or anything else going on, and a clean gas comes out at the top. So what this lecture is going to focus on is how these packed columns work and how to design them. And the idea is that you want very good vapor-liquid interface contact in a large amount of surface area so that you can get the separation to happen. But the challenge is that there's no individual stages or trays that are defined here. You have this continuous packing, and there's separation happening throughout that entire bit of packing. There are a few types of packing available. These are just a few examples. If you search online or look in Wonkot's book, you'll see examples of more. They have names frequently that are people's names or company names, like these are Raschig rings, that's named after Raschig. Basically, it's a piece of ceramic, a ceramic tube, which gets cut into little fragments. And then when those get dumped into a column, liquid flows on the inside and outside of all those little rings. And vapor can flow through the inside and outside also, so you get good contact. You also have saddle-shaped packings that allow a lot of contact. These are burl saddles here. Interlock saddles. These are also interlock saddles, but they're made of plastic. And basically, depending on your application, different types of materials might be better. Like if you have high gas flow rates, you may need a more dense material, so ceramics may be preferable. But if you have a very caustic solution, you may need to use plastic in order to avoid corrosion of that packing material. So when we design a packed column, we need to balance the flow rate of liquid and gas so that we have a steady flow of liquid down through the column while at the same time getting good contact with the vapor that's flowing up through it. And there's this figure on the right that illustrates the amount of liquid held up in a column, and this is in units of volume per volume, so cubic meters per cubic meter, as a function of the superficial gas velocity. And that is the volumetric flow rate of gas through the column divided by the cross-sectional area. So it has units of velocity, but it represents the average rate at which vapor is flowing through the column. And what you find here is that if you look at different liquid flow rates, and that's what's being illustrated here, these are different superficial liquid velocities. For example, 5 meters per hour, 2.8 meters per hour, 10, 20, 40, 60, 80. You basically see very little dependence of the liquid holdup on the superficial gas velocity up to a certain point. And that's because there's enough space available that the gas can flow up and the liquid can flow down, and there's no problem. But we can reach this point, which is called loading. And that's illustrated with this dashed line here. That's where you begin to see liquid accumulating in the packing. So that's referred to as loading. And now you have more than you would have if you had good flow. So basically the gas is flowing fast enough that you're starting to push up a little bit of liquid and you're accumulating volume. And a little bit of that's okay. But what you find is that there's a point called flooding, and it's illustrated here, where you get to a high enough vapor velocity that it starts to actually push liquid out the top of the column. And you can't operate it that way because it's not going to operate at steady state. Basically, you're going to accumulate liquid and it will eventually come out the top of the column. You may find this happening when you actually do the packed column lab experiment next year. And it's dramatic, but it's not desirable. So a lot of design correlations for packed columns are based on that flooding velocity and how close you are to it. So if you're, for example, 80% of the flooding velocity, you'll be far enough away, maybe over here, that on the top line, so that you can avoid any problems associated with flooding. And a lot of the characteristics of what you see on a chart like this depend on the packing characteristics. So some of the things that are important that are shown over here on the right include epsilon. That's the void fraction. That's basically the fraction of the volume of the column that is empty space. Notice that here it's 0.94. So only 6% of the column actually has solid material in it, in that packing. And that's typical. You have a very, those shapes on the previous slide, when you dump them into a column, they leave a lot of empty space behind. There are also characteristics. DT, I believe, is the diameter of the packing, but it's the effective diameter. So it's the diameter of a sphere with the equivalent surface area. LT has to do with, I believe, it's the column diameter. So all those characteristics are important. Also, what material is in the column is important. So the viscosity of the fluids and other characteristics can influence this. So you'll find charts like this for specific types of packing, and you may have to look for different charts or different correlations to be able to say what happens. So there are two ways to design packed columns. One is based on what we already know how to do, so I'll start with that. It's called the height equivalent to a theoretical plate, and it's based on assuming that we can do the design as if we reach equilibrium on every stage. So we can do this for distillation, we can do it for stripping, and we can do it for absorption. And the idea is that we define a height equivalent to a theoretical plate. This is the height of a specific type of packing that is required in order to do the separation that would be done on a single tray. And so what we find is that if we look as a function of this F factor, which depends on the superficial gas velocity divided by its density, so it's UV over rho V, the 1/2 power, the height equivalent to a theoretical plate for this particular packing and for this particular mixture, which is cyclohexane and N-heptane, we basically don't see a strong dependence on that velocity. So it's basically constant across a wide range of conditions. And then we reach the load point and all bets are off and it begins to increase significantly, but you probably wouldn't want to operate the column that way anyhow. So this is a very easy way to do packed column design, and you really don't need to think about it more other than to find out what that HETP value is. If you need to determine what it is, there are two approaches. One is to use this correlation, which is from Woncott. It's basically saying that the height equivalent to a theoretical plate in units of meters is 100 divided by A sub P to plus 0.1 meter. A sub P is the total area of packing per unit of volume. So that's a parameter that you can't calculate yourself. You have to be told what it is, and a lot of times manufacturers will tell you that in the spec sheet for the packing material. You can also find correlations like this where you have HETP reported for a particular packing material, but what's more common is to have to do an experiment. So you might be asked a question, for example, where you have a packed column of a certain height, say it's 6 feet of interlock saddles, and you're told that it does a certain separation. It removes 90% of a particular solute, say ammonia, out of the liquid phase by stripping, and you would have to calculate how many theoretical stages that corresponds to do that separation, and then you can use the height to figure out what HETP is. So that's what you would do experimentally. So if we think about a design procedure for a packed column, we would begin by doing a McCabe-Thiele diagram or a Fensky-Underwood-Gilliland correlation, or using the Kremser equations. I didn't list everything, but you do the equilibrium calculations as you always have done, and you assume ideal stages, and from that you determine the number of ideal theoretical stages required inside of the column. If it's a distillation column and it has a partial reboiler, remember to take away that stage before you do anything else. Also keep fractional stages. You don't need to round up because you can have a fraction of a full stage in a packed column. So just keep the fraction, and if you have to estimate from a graph, just do your best. It'll be okay. Then use HETP to convert to the height of the column. So the height is equal to HETP times the number of stages. And it's just that simple. So that would tell you the height that's required. Another aspect of the design of a packed column is to determine the column diameter. And that's based on the tolerable pressure drop that you can use in your column. Anytime you have liquids flowing through this high surface area packed material, the pressure drops very quickly. And so you need to pick the diameter of the column so that the superficial gas velocity will give you the pressure drop that is acceptable to you. Obviously, you would like to have the lowest pressure drop you can get away with, but that usually means that you would have an unacceptable rate of material of mass transfer between the liquid and vapor phases. So something like 0.25 to 0.4 inches of water per foot, and you can convert that to other units, of course, if you prefer metric units, but that's generally the order of magnitude of what's considered to be acceptable in a packed column. So what you can do is take a chart like what's on the right, and what is being plotted here is pressure drop on all of these curves. So each one represents inches of water per foot of packing. And the axes, notice that they collect a number of variables, but this X value includes L and V. So that's the total liquid flow rate and the total vapor flow rate. Also the molecular weights, ML and MV, and the densities of the vapor and liquid. Those all go together on that axis. And so basically, if you know L and V because you did your design, you could calculate the value of X from the substances that you have. And then you can take that, choose what pressure drop is acceptable. For example, if it's 0.3 inches of water per foot, that's the orange highlighted curve. And then take your value of X, which you would get from your design, and find out what the vertical axis needs to be. So for example, it's here 0.025 or whatever it happens to be. And notice that it contains a few other variables, but the most important one is the superficial gas velocity, U sub V. So you can read off from that what the pressure drop needs to be. So that's one approach. And so once you know that velocity, if you know the total volumetric flow rate, which you can get from the molecular weight and the density of your vapor, you can then use that to calculate the cross-sectional area that's acceptable, and then calculate the diameter of the column. What you'll do in the chemical engineering lab is to look at how pressure drop depends on flow rate in a column. And if it's a dry column or it has a single fluid in it, the Ergun equation is a good correlation between, this is the pressure drop on this axis, so it contains delta P over L, so that's the total length of packing, the pressure drop over that value. And it also depends on some other characteristics. For example, epsilon appears here. That's the void fraction of the packing. There are other characteristics that appear in that. And on the vertical axis, we have the Reynolds number. So that depends, it has UV in it, and I'm going to circle it, even though I'm using my finger, it's not perfect. So there's the correlation here between pressure drop and superficial gas velocity. So you could decide what velocity to use to get to a certain pressure drop. Countercurrent flow. If you have liquid coming down through the column and vapor coming up, as is more typical for something like absorption, or actually all the separations we're trying to do, you need different correlations. And one example is the Leva equation. This relates delta P over Z, so that's the pressure drop per unit length of column, to L prime and G prime. That's the liquid flow rate and the gas flow rate, expressed as mass per time per square foot. So it's actually a flux. It's the amount of material moving per unit of time per square foot of cross-sectional area of the column. It depends on the gas density, but then there are two parameters that define what happens for a given packing. So it depends on the size of the packing and the type of packing and the material that it's made of. Alpha and beta are parameters that go into this equation and are found experimentally, and will just tell you the relationship between pressure drop, L prime, and G prime. Usually the dependence on L prime is weaker than the dependence on G prime. So you may find that beta is small enough that you can basically ignore the dependence on liquid flow rate and just focus on G prime, and basically find a diameter so that the area of the column is going to depend on the total volumetric flow rate and G prime, and you can use that to figure out the cross-sectional area and therefore the diameter of the column. So that would allow you to do a complete design, and you could say my column needs to be 6 feet of packing, 2 feet wide, and go from there and do your design. That's not the only approach to designing packed columns. The other approach is rate-based. And the reason that we use a rate-based approach is that what actually needs to happen is that you get transfer of material from the liquid to the vapor, or from the vapor to the liquid, depending on which type of separation you're doing. But in a real column, that rate of mass transfer varies through the column, but it dictates what's actually going to happen. So basically, this is a completely different conceptual approach to the equilibrium approach, but we'll relate it to equilibrium as we go through our derivation. So the idea is we start with the two-film theory, and I had introduced that in class. It's discussed in chapter 15 of Woncott, where he talks about mass transfer in general. The idea is that we assume that we know the bulk concentration of a solute in the liquid phase and the bulk concentration in the vapor phase. And when we look at what happens at the interface between the two, we assume that there's a thin layer of liquid through which there's actually a concentration change, and there's a thin layer of vapor through which there's a concentration change. And at the interface, the two phases are truly at equilibrium with each other, but away from that interface, diffusion dictates what's going on. So the way that we analyze this is we can calculate the flux through that liquid interface by assuming that we have steady state flux, and we know the concentration at the interface, which is Ca in the liquid phase at the interface. So if we assume that we know that, and we know the concentration in the bulk liquid, we expect to have a linear concentration profile, and therefore we can write this expression for the flux. So it's the opposite of a diffusivity times the concentration difference over the thickness of the interface. And we can rewrite that by taking the total molar concentration in the liquid phase and write it in terms of mole fractions. So this is going to be what we're going to use. It's the diffusivity times the total molar concentration in the liquid over the thickness of the liquid interface times XA minus XAI. Similarly, in the gas phase, we can write a similar expression, just making the same types of assumptions. So the molar flux in the vapor phase through that interface is given by this expression. So it's the diffusivity of solute A in surroundings B, so the solvent B, in the vapor phase times the total molar concentration in the vapor phase over the thickness of this layer times Y at the interface minus Y far away from the interface. So we have expressions that we can write for flux. Now, what good does that do us? Well, we're going to first of all admit that we don't actually know the thickness of that interface. It's conceptually helpful to think of it as being what it looks like, but we don't actually know what it is. So we're first going to define mass transfer coefficients. So a mass transfer coefficient is going to allow us to write flux in terms of a driving force multiplied by that mass transfer coefficient. So in the liquid phase, we're going to write lowercase k sub x representing the mass transfer coefficient in the liquid phase in terms of mole fractions. And it actually includes the mole fraction at the interface as part of the definition. Notice that it contains the diffusivity, the total molar concentration, and the thickness of the liquid interface. And we define a similar mass transfer coefficient for the vapor phase in terms of mole fractions. And the flux is going to be written as that mass transfer coefficient multiplied by a driving force for mass transfer. So the bigger the difference is in mole fraction between the bulk fluid and the interface, the faster you expect mass transfer to actually happen. Also, the higher the mass transfer coefficient, the faster mass transfer happens. So our flux expressions now look like this for the liquid phase. So we have Kx times XA minus XAI. And for the liquid phase, we have Ky times YAI minus YA. Notice that the signs are different, and that's intentional. That's not a mistake. That's because we have the flux moving in a particular direction, and it's moving from the liquid to the gas the way that I defined it. We could switch the axes around and change the signs for both fluxes, and it would be the same idea. So the sign doesn't matter as long as they're consistent with each other. Now, another thing that we want to do when we do our design is we don't want to actually base it on flux, because the flux depends on the interfacial area, but we don't know necessarily what the interfacial area is of our column. It's because that's the area of the actual packing surface. So what we do is we multiply the flux by the interfacial area per unit of column volume, and that will give us a rate of mass transfer per unit of volume in the column. And that's going to be the most useful way of defining mass transfer for us later on. So we're going to let A, the variable A, it's a lowercase variable, represent the interfacial area per unit of volume for a particular packing in the column. And then we can write the rate of mass transfer as Kxa, for example, multiplied by Xa minus Xai. So that would be the driving force. And instead of just having Kx on its own to define a flux, when we multiply by lowercase a, now we get a rate of mass transfer, number of moles per unit of volume, per unit of time. And we do a similar thing for the gas phase. We multiply by lowercase a. So what you're going to find is that the mass transfer coefficients are frequently written as a product of a flux type of mass transfer coefficient and A. So don't get confused by that, but you'll always see the A going along with the mass transfer coefficient. What we have so far is two ways of writing the rate. One for the rate that's happening in the gas phase, and the rate that's happening in the vapor phase. Vapor phase and liquid phase. And those two have to be equal to each other at steady state. So that's why I've written them as being equivalent. It's nice to have, but it turns out that it's not actually possible to solve problems with that because we don't know the interfacial compositions. So they're conceptually useful, but we don't automatically know what they are. So to get around that, we want to define some new mass transfer coefficients and new driving forces. Now that we have this idea of driving forces established, we're going to say that we can define any kind of driving force we want as long as we can relate it back to something that has a greater physical meaning. So what we're going to do is, instead of using the difference between X in the bulk phase and the interface, we're going to define our driving force to be the difference between X in the bulk phase and X we would have at equilibrium with the vapor if it was actually able to reach equilibrium. This is sort of conceptually related to the idea of the Murphy efficiencies, where you use the difference between what you would have at equilibrium and where you actually get in the process of going through a particular stage to define an efficiency. Here we're just saying that the rate of mass transfer depends on how far we are from equilibrium. And that makes some conceptual sense, although it's unclear what that has to do with our physical picture of what's happening at the interface. But we'll come back and define that. So we're going to define a new mass transfer coefficient, and to be consistent with Wonkot and other sources, we'll call it capital Kx, and it's multiplied by A, and then that's multiplied by this difference between the bulk mole fraction and the mole fraction we would have at equilibrium. And that's going to define our new rate. And then similar for the vapor phase, we have a new mass transfer coefficient, capital Kya, and a driving force Ya star, what we would have in the vapor phase at equilibrium, minus the actual composition that we have in the vapor phase. So we're allowed to do this. Like I said, we can define any consistently defined driving force that we want for mass transfer, and as long as we can define a mass transfer coefficient to go along with it. But in order to give it more physical meaning, we're going to let M be the slope of a y versus x curve at equilibrium. We also called this K earlier in the course, so I'll just say that's equivalent. I'm doing what Wonkot does, which is to use M. I guess the reason that he does that is that because M may vary as a function of position in the column, and you can account for that. But a lot of times we assume that it's constant. So if we do that, and we go back to these definitions of rate from all the previous slides, we can first of all take this definition from above and rewrite it. So if I take that rate on the right-hand side and I divide it by capital K, y times A, that's equal to Ya star minus Ya. So it's just the driving force for mass transfer. And I can also rewrite that by adding and subtracting Yai. Now, it's not entirely clear why I'm doing that yet, but I'm allowed to do it mathematically. So on the next slide, I'll show why I did that. If I take that, and now I assume that, first of all, Ya star is equal to M times Xa, and that's just by definition of what the star means. It means what Y would be if the system was able to reach equilibrium. And then we're also going to assume that the two phases are at equilibrium at the mathematical interface between them. So the point at which Ya and Xa are defined, those two are at equilibrium with each other. So that allows me to write Ya at the interface as M, the slope of the Y versus X equilibrium curve, M multiplied by Xai. So if I can do that, I can substitute X values into the expression on the previous slide that was at the bottom. So now I can write the rate over Kya, capital Kya, I should say, as being Ya star minus Ya, but that's the M value times Xa minus Xai plus Yai minus Ya. Now the Xa minus Xai should look familiar because that's a driving force that was on a previous slide. That was the original driving forces that we defined. So I can also write the rate of mass transfer divided by the mass transfer coefficient that goes with that driving force, lowercase kxa, as being equal to xa minus xai. And I can also say that the rate over lowercase kya is equal to ya at the interface minus ya. So if I use these expressions and substitute each one into this equation, what I'll get is that the rate over kya is equal to the rate over kxa times m, because m appears in this expression, so m appears here. So I get rate over kxa plus the rate over kya. And each of these depends on the rate of mass transfer, so it's the rate per volume per time, but those are actually all the same. Because we're talking about the same column, it's the same solute, and it's one process. It's mass transfer from one phase to the other. So I can eliminate those rates because they appear in every term, and what I get is this final expression that 1 over capital Kya is equal to m over lower kxa plus 1 over kya. So what I can do now is if I actually knew the value of lowercase kx and lowercase ky, I can use this expression to calculate what uppercase ky is. So I can derive expressions like this for all of the mass transfer coefficients I can define in my system and relate them to each other. So if I know one or a pair of these values, I can calculate another. And so that's useful for doing problems and for using correlations. So that gets rid of the interfacial compositions, and it also gives me a way to define these capital Kx and capital Ky mass transfer coefficients. So if we go through a similar derivation, we could show that for the liquid phase, 1 over capital Kxa is equal to 1 over lowercase kxa plus 1 over m times lowercase kya. Notice that the slope m appears in the denominator here. It appeared in the numerator in the previous expression. That's not a mistake. That comes out of the derivation. You can also define mass transfer coefficients based on partial pressure differences, concentration differences instead of mole fraction differences, and mole ratio differences, capital K and capital Kx and capital Ky, if necessary. So for example, you can write the rate as a capital K uppercase Y multiplied by the difference in uppercase Y star minus uppercase Y. So here, you'd be using mole ratios instead of mole fractions. And that lets you do design based on, for concentrated systems, based on mole ratios. Another thing that you can do, in addition to what's illustrated here, where we have a relationship between the mass transfer coefficients, is we can also use those mass transfer coefficients to see where the interfacial compositions actually ought to be. So if this is my operating line, and if I have a value of x and y on that operating line, and this is my equilibrium curve, so I've got the theoretical, for example, if I have this particular value of y, the x star value that goes along with it would be here. And that just comes from the distance between the operating line and the equilibrium curve. But if I know what my mass transfer coefficients are, I can move just a fraction of the distance from x to x star, and based on how far I go, it's going to depend on the mass transfer coefficients. So this line that's drawn here, this diagonal line from A to B, has a slope of negative kxa over kya, and you can show that the intersection of that with the equilibrium curve actually gives you the interfacial compositions. So this illustration can also be used to relate the compositions at the interface to the equilibrium concentrations that you would have at equilibrium. So it is possible to say what the interface concentrations are, as long as you know what the mass transfer coefficients are. But we don't always know that. So it's not usually going to be our basis for design, but it is a way that we can physically understand what's going on in our system. With that in mind, now that we've gone through all of this, we're actually going to use our rate expression and derive an equation for saying how tall a packed column needs to be to do a given separation. And so we're going to do a material balance over a thin slice of packing. And I'm assuming that we're basing this on the mass fraction in the vapor phase. So this would be most directly applicable to an absorption column, where the absorber is lowering the concentration of Y, or the value of Y, as we move through the column from the bottom to the top. So that's the assumption here. And so we can define a thin slice of material. It has a thickness of dl, lowercase l, and that'll just be a thin slice normal to the direction of flow. And we have y coming out of the top of that slice and x going into that slice on top. And we assume that y changes a little bit as a result of going through that little slice of packing. So we can define y plus dy to be the y value that comes out of that slice of packing plus the difference in what went in. And then x plus dx represents the change in x because of that little slice of packing. So if we define our terms that way, we can do a material balance over that slice of packing. So we'll take the gas flow rate in. We take the total gas flow rate multiplied by y plus dy. That would represent the solute flow rate that's coming into that packed column minus the flow rate out multiplied by the mole fraction leaving that slice of material. And we're using lowercase x and y, which implies that it's a dilute system. So G and L are not going to change significantly as a result of what's going on in this packing. So this represents the change in the gas phase, and then we're going to relate that to the rate of transfer out of the gas phase into the liquid. And rather than trying to draw something that depends on x and the value of L, we're actually going to directly calculate the rate. So the rate comes from the mass transfer coefficient, and it's given by uppercase ky times A times y star minus y. So that's the driving force multiplied by the mass transfer coefficient. That's going to say how quickly solute goes out of the vapor phase and into the liquid phase per unit of volume per unit of time. And then we multiply it by the volume of this little slice of packing, dV. If we know the cross-sectional area of the column, we can also write dV as S times dL, which is what's on the very right-hand side of this equation. So this would represent a material balance based just on what's happening in the gas phase. We could write a similar balance based on what's happening in the liquid phase, but we don't need that right now, so we're not going to do it. So if we rearrange that expression, we can gather together the terms that depend on y on one side of the equation. So we have dy over y star minus y. I eliminated g times y from the left-hand side of the equation because that term is the same in both terms. So that's one side of the equation, and the other side of the equation is capital Kya times S over G times dl. So we have differential quantities appearing on both sides of this equation. So that should mean that we can integrate both sides of this equation as long as we can define the terms. So the left-hand side, and we need boundary conditions to do that. So on the left-hand side, I'll be assuming that we know the value of y going into the column, and I'll just call that y in. So the mole fraction in the vapor phase going into this packed column at L equals 0 is known. And we also assume that we know the value of y at the outlet of the column, and that's at L equals h. So at the entire packed column height. So if I integrate, I'll be integrating the left-hand side from y in to y out of dy over y star minus y. And the right-hand side, I'm integrating from 0 to h of this quantity, which actually is a constant, times dl. And because ky as over g is a constant, that integration is very straightforward. It's just L evaluated from 0 to h multiplied by those constants. And so the right-hand side can be evaluated right away. So I get ky times a times s over g multiplied by h. Now what we actually want to know is what height of column is required in order to go from y in to y out. So I'm going to rearrange this expression to solve for h, because that's the thing I actually want to be able to calculate. I can rewrite h as a new quantity. I will call it NOG multiplied by h sub OG. And these are new variables, and they have names. So HOG is the height of a transfer unit. This is like the height of a stage, but it's a slightly different quantity because it's based on mass transfer coefficients. And based on the derivation on the previous slide, I can just write what its value is. So it's the gas flow rate divided by the mass transfer coefficient times the cross-sectional area of the column. So that's very straightforward to calculate as long as you know the mass transfer coefficient. Although you may need to determine that experimentally. And you can actually work in reverse to figure out what HOG is. The other quantity that appears here is a number of transfer units. And again, transfer units are an abstract concept, but they're kind of like stages, but defined for mass transfer-based problems rather than equilibrium-based problems. So here, the NOG, the number of transfer units in the gas phase, is equal to the integral from y in to y out of dy over y star minus y. But because y in is greater than y out, I can rearrange this equation, just change the limits and multiply by -1 in order to get something that I can numerically integrate and it'll make sense. So that's this quantity. So it makes the most sense to define the number of transfer units as the integral from y out to y in as dy over y minus y star. A transfer unit, again, is an abstract concept. It's like a stage, but it has to do with mass transfer. So just remember that. You'll just have to get used to that idea, that it's this abstract concept. And there are actually different ways to define it. You just have to use it consistently. So if I use a different type of mass transfer coefficient, I would define a different transfer unit. And there's actually a table summarizing that I'll get to at the end of this presentation. Also notice that this number of transfer units can be calculated numerically or analytically depending on how y star depends on y. And it looks actually very similar to what we have in batch distillation, where we had the difference between the mole fraction in the liquid phase and the mole fraction in the vapor phase. So with that in mind, if we do have a constant relationship between y and x, so if this slope of the equilibrium data, y over x, which is equal to m, if that's constant, then I can integrate that expression and get a symbolic expression as a result. So if I let A be equal to the liquid flow rate over m times the gas flow rate, and that's the same absorption coefficient we used previously for the Kremser equations, if I know that value, then I can analytically solve for the number of transfer units, and I get this expression. In dilute systems, it's common to have a constant value of m, so it's common to be able to use this expression. So you should be familiar with it and comfortable with it, but that's the way to get the number of transfer units based on what's happening in the gas phase, so based on the rate of mass transfer in the gas phase. Some things to keep in mind is that you actually can relate the number of transfer units to the ideal number of theoretical stages under certain situations. So if the operating line and the equilibrium line, if they're both straight over the range of mole fractions we're interested in, and if they're parallel to each other, which would mean that m, the slope of the equilibrium curve, is equal to L over G, that's the slope of the operating line. If that happens to be true, it's possible to show that actually the number of transfer units and the number of theoretical equilibrium stages are the same. I'm not going to show that, but you can show that. So as long as m is equal to L over G, what you get from the rate-based analysis and the equilibrium-based analysis are exactly the same numerically. If the two lines, if the equilibrium line and the operating line are straight but not parallel, you can show that the height equivalent to a theoretical plate is equal to the height of a transfer unit times the log of 1 over a over 1 minus a divided by a. So if you evaluate that expression, you can relate HETP to the height of a transfer unit. And also, if they're straight but not parallel, the number of transfer units can be related to the number of theoretical stages based on the value of a. But these relationships only hold as long as you have straight lines on your y-x diagram, which would imply that you have a dilute system. If you don't have a situation where m is constant, so even though it's dilute, and even though the change in mole fraction due to, the change in composition due to the change in mole fraction is small enough that L and G are constant, you can still evaluate the number of transfer units based on numerically integrating the expression from the previous slide. So keep that in mind. You can always fall back on that approach. And then finally, I want to conclude with this table, which describes other types of driving forces. And this shouldn't overwhelm you. It's basically the same concept being applied to mass transfer in different phases. So what's shown here are different driving forces. So the one that we used was y minus y star. So we're assuming that mass transfer is limited by the rate of what's happening in the vapor phase, and we're using a driving force based on the equilibrium composition. the Y star value. So HOG is the height of a transfer unit that goes along with that, and NOG is the number of transfer units that goes with it. And you can see that the definition of those is consistent with what we just talked about. But there are other definitions. So you can have a driving force based on the difference in partial pressure. But notice that the height of a transfer unit doesn't change, although the mass transfer coefficient does. And the number of transfer units is also similar, but it's based on the partial pressure. We can define a driving force based on capital Y values, so mole ratios, in which case we need to be careful about the variables that we use, but we still use HOG and NOG as the height of a transfer unit and the number of transfer units. If we base our calculations on the interfacial composition, we use different symbols, HG and NG, as the height of a transfer unit and the number of transfer units, and those are different, and you would actually have to have some way of knowing the interfacial composition to calculate the number of transfer units. And then down towards the bottom of this curve, there are HOL based on the difference in the liquid phase, so the difference between the equilibrium value and the actual value in the liquid phase, and then HL based on the interfacial liquid phase composition and the actual mole fraction in the bulk phase. So you can read Woncott to find out more about all these driving forces and how they're related to each other, but I'm just going to leave it at that for now. These are actually coming from Cedar and Henley, but they are discussed in Woncott's book as well. So basically, this is all that you need to know to be able to do mass transfer calculations in packed columns.